All right, so this is the first exercise. We are given a shaft, a solid shaft made of aluminum with a diameter of 80 millimeters and shear modulus of 26 gigapascal. It is subjected to a torsional loading as is shown in the picture. You want to calculate the angle of twist at A. Again, when a problem like this is given, you need to always be careful about two things. The first thing is that when you want to calculate the angle of twist, you need to always think of with respect to what, okay, or where. And that where is usually a fixed point, or it better be a fixed point because then it makes sense, right? So here we say angle of twist at A, but actually we are asking from, let's say, A with respect to C, because C is the fixed point, okay? Now, when you write A with respect to C, it basically means from C to A, okay? So in this case, the best coordinate system, or the most natural way of thinking of your coordinate system, is such that it starts from point C and it goes to point A. All right? Then it makes sense. Because remember, this formula for the angle of twist, you know, somewhere you would say you have an integral from C to A, right? And then in that integral, if you don't use the coordinate system properly, then you would need to be careful about the minus sign. You get something strange there. So to be consistent is, I think, the most important part in this sort of questions. And we do exactly the same thing. So for this problem, we want the angle of twist at A. So we would choose our coordinate system such that it goes from C to A. So angle of twist at A is basically A with respect to C. And then instead of A with respect to C, you can say A with respect to B plus B with respect to C. Does that make sense? Now, B with respect to C means from C to B, and in that portion you have a distributed load. So here you definitely have an integral. So here you would have an integral from C to B of t as a function of x divided by gj dx. All right? But from B to A, t is constant. I mean, you can think of it as integral also, but because that t is constant, you can immediately write it as, you know, t of AB, or BA rather, length of BA divided by GJ. Okay, so it's important to kind of appreciate this, what's happening here. So all we need to do is basically now to find out what is t as a function of x. You know, g and j is constant. G is given, it's 26 gigapascal. J, you know, it's a circular shaft with a diameter 80 millimeters, so that's not difficult. So G is 26 gigapascal. J is pi over 2, let's say 40 millimeters to the power 4. It's the same here, it's pi over 2, 40 millimeters to power 4, and this is 26 gigapascal. Length from B to A is 0.6. From C to B, obviously, we have an integral. Is that all clear so far? Okay, so the only thing we need to do now, or the most important thing, is to find this Tx. Now, if you want to find the torque distribution or internal torque distribution, by the way, pay attention, this is internal, right? When you want to find the distribution of that, we need to draw our free body diagram, starting, let's say, from point C to a certain cross-section at X. Okay, so we are going to basically cut this thing at, let's say, at a cross-section at a distance X. So let's say here, I'm going to cut this at this distance X. And we want to find out what is T there. Again, for simplicity, I'm going to draw this in 1D now to make it simple for us. If it is 1D, and then this would be your point C, and this is point A, this is point B, and see, here at X, at A, you have a moment that is clockwise, right? So it looks like a minus if you think of your coordinate system being like this. So at A, you have a more, let's say, external torque which looks like this. Does that make sense? From C to B, they are all also, a few little minuses, but it's a distributed torque, right? So you kind of expected that at C, you would have a torque which is positive, okay? All right, so I'm going to draw it like that. And let's say this is TC. And I am assuming, basically by doing that, I am assuming that my TC is counterclockwise, right? It's the external one. So this is TC then. And then again, I am emphasizing this is external. All right, so if for this system, if you want to just, let's say, write your equilibrium here, you would say TC, it with a plus, because our plus direction is towards, let's say, our X direction. So it would be plus TC minus integral of these distributed loads. But since they are constant, we can just, instead of integrating, we can just multiply that 10 by the distance, by the length, right? So it would be minus 10, and then they are in kilonewtons, so we have it power 3 times 0.6. Okay, so this is all the torque you get from them, and then this is the torque you get from A, which is also coming with a minus, and it's also kilonewton, so that's that. So from this you get, again, this is external. From this you get TC equals, well, 8 kilonewton meter. Does that make sense? Now, this is the external one. What does that mean? It means when you want to still use this T, you need to find its relationship with this external torque. Okay, so we need to draw one more of these diagrams more carefully. Now, this is point C. We know you have 8, okay? And then we have this little distributed force. So what we want to do is to cut it at a distance X. Okay? So if you cut this at a distance X, now your Tx, remember we said this is our convention. Now this is our internal T that we are talking about, right? Our Tx plus that 8 minus, whatever you get from these little things, which is 10 times, okay, we write 8 in kilonewtons, so let's write all of this in kilonewton meter. Okay, so this is kilonewton, times x equals 0. Does that make sense? So tx becomes minus 8 plus 10x, which makes perfect sense. So see, you get a minus. Now, that means at the very beginning, at x0, your internal torque would be minus 8, which makes perfect sense because you have 8 on the outside. You need the opposite of that to be on the inside, right? So the internal torque. Okay, so this would be your relationship for t. Now, also to make it more clear, we can always draw our distribution of torque in the system, and I strongly recommend you do that. So let's say this is T, and it's internal, by the way. At point, this is C, this is B, and this is A. So if you want to draw it, it's going to look like this. It's going to be minus 8 at C. Then with this line, minus 8 plus 10x, it goes all the way for x between 0 and 0.6. So if x is 0.6, then it becomes it becomes minus 2, right? And then between b and a, it's just constant. Okay, so this is your distribution of internal torque. We have basically everything we need to have for this problem. All you need to do is to insert that t in this equation and integrate it from c to b, and then just add it with this one, and you're done. Okay, so angle of twist from A to C is, A with respect to C would be A with respect to B plus B with respect to C. And as we discussed, for the second part, you just simply have our relationship here. Now, you know T is minus 2, right? The internal T is minus 2. So for the second one, you just have that constant relation minus 2 times, again, in kilonewtons, so 10 to the power 3, divided by Gj. And the length is 0.6, right? Divided by Gj, plus integral from, say, 0 to 0.6 of minus 8 plus 10x times 10 to the power 3. Again, this is kilonewton, divided by Gj dx. And what you need to do is to, okay, you can take the Gj out. So you get minus 1.2 here times 10 to the power 3. From the integral, you get, let's do the integral together a little here. So this would be minus 8x plus 5x squared from 0 to 0.6. So at 0, it just gives you 0. At 0.6, this gives you minus 4.8, right? And the other one gives you plus 1.8. So altogether, this gives you minus 3. And then again, it's kilonewton, so it's 3 to the power 3. Okay, so this would be minus 3, 10 to the power 3. Does that make sense? Okay, so this would be nothing but minus 4.2, 10 to the power 3 divided by Gj, which again, you can calculate Gj. I mean, we just wrote it. G was 26 gigapascal, and it's a solid shaft. You use the formula for solid shafts. And if you insert Gj for that, you get your phi of A with respect to C to be minus 0.04017 radian, or minus 2.30 degrees. And you can pay attention again, it's minus, but its sign being minus shouldn't be a big surprise. You see, the way you apply the moments, they are clockwise. And clockwise for us in our convention means minus, right? So it's not a big surprise that, let's say twisting something clockwise will cause a clockwise angle of twist. That's the idea. So minus just means it is clockwise. Do you have any question? All right, so this was the first one. The second one is this. Also a similar exercise, but because I know these exercises are usually difficult and less intuitive, I think we should have a few of them. So this is the next one. We have a steel bolt with the shear modulus of 75 gigapascal, tightened with a hole, so that the reactive torque on the shank AB can be expressed by this equation, T equals kx squared. Again, this is a distributed load, so you see the unit is Newton meter per meter, or just Newton. If a torque of 50 Newton meter is applied, as shown here, determine the constant K and the angle of twist in the shank. The shank has a constant radius of 4 millimeters. All right, so what you want to do is, again, to just think about it in our usual terms. The most important thing in this particular problem is to pay attention that the x direction is starting from this. Okay, so when you write, in this example, when you say phi b with respect to A, it makes sense. So basically, it means the left side with respect to the right side. Does that make sense? So it's in accordance with the coordinate system. Okay, so we proceed exactly as before. We write our equilibrium equations to get the internal torque, and then we integrate that internal torque through the bolt to get our, let's say, angle of twist. So that's what we want to do. But there is a little interesting part here, that this K itself is unknown. So the K itself shall be also calculated from equilibrium. Does that make sense? So we write our equilibrium of external forces, external torques. From that, you get our K, and then after we have K, we write our internal torque, we integrate it, we get the angle of twist. That's what we want to do. So let's begin with the external system. All right, so if you look at this system, let's say this is our bolt, and then you have this, at this end, you have the torque of 50 Newton meter. And then you have these little opposite torques, or the distribution in this fashion. All right? Now, if you cut this at a certain distance, so this is point A, let's say you cut it at a certain distance x, we can also have that, that T at C, right? And this would be, let's say, our coordinate system. Okay, so if you just write the equilibrium for this, what do we have? We have TC, right? Does that make sense? What's that? Well, let's say this comes all the way here, and then we end up at B, okay? So C is just a point at a distance x. It's an internal point. So let's say this is point C. And then pay attention to the way that we just draw the torque. It's counterclockwise at C, right? So it comes with a plus, and it's internal. So it's internal, but it's also counterclockwise according to our coordinate system, right? So x is in, if you look at it in our usual system, it looks weird. It looks clockwise, but pay attention that x is in this direction. So you should look at it this way, and that's counterclockwise. Okay, so that's TC. Then you have TA minus the integral from 0 to x of that t dx. Does that make sense? Okay, so this is what we have. Now, t itself is kx squared, all right? So you can just basically calculate t so this is our internal t, right? So our internal t at any x plus ta, which is 50, minus integral of 0 to x of, kx squared dx is 0. Okay, so that tells you tx is minus 50 plus integral from 0 to x of kx squared. Now, integral of that is kx cubed divided by 3. So it's k divided by 3, x cubed from 0 to x, right? And then at 0, it's just 0. At x, it's basically x. So this gives you t as a function of x. This is our internal torque. Okay? So basically, it tells you that if you wanted to draw the graph as we usually do, we have torque with respect to x. So if this is our x coordinate system, again, pay attention. X is, in the example, x is drawn like this, but I'm just write it like that. So 0 means here, I don't know, 25 means here, and then 50 means here. So they are kind of the opposite in that sense, but that shouldn't be a big confusion. So you have t as a function of x. It's minus 50 minus k over 3. Sorry, I have I think it's plus, sorry, it's plus 50. What? No, it is, what have I done? Something is off. This is plus, right? Yeah, okay, so it's minus 50 plus k over 3 x cubed. Okay, now, if you plot that, it starts from here at point x0, which is a, and then you have a cubic function like that, and then I don't know, if you want, maybe you plot it like that. Okay, so this is the curve, minus 50 plus k divided by 3x cubed. Now, this gives you your t at any point x. So if you want t at any point x, you have it. Okay, so if you look at this picture, and it brings us back to your question, what would it be? What would be the internal torque here at this end? Which point would it be? It would be this point, right? At the very end, we will have a torque of 0, right? So the equilibrium is achieved. all of the internal, let's say, the internal torque is now completely compensated for. Does that make sense? So in other words, well, maybe you can think of it as if you would cut it from the left-hand side. You know, at B, you don't have external torques, right? So just the point next to B, the internal torque has to be 0, right? So you remember, internal and external, they should cancel each other. So basically, this is point B, okay? In other words, if you're in your T equation, if you assume x is equal 50 millimeters, then you want this to be 0, which is point B. And from that, you just, you know, you would say minus 50 plus k over 3, and then 50 is millimeters, so it's 0.05 to the power 3, 0. That gives you k equal 1.2 10 to power 6 Newton per meter squared. Also, dimension matters, right? Okay, so now we know what is that constant that we didn't know. From the equilibrium, we know that constant k is 1.2 times 10 to the power 6, right? So the next thing you want to do is to calculate the angle of twist, right? So the angle of twist from, let's say, from A to B, it would be B with respect to A. So we do exactly as we did before. So angle of twist, again, this means from A to B, which is in accordance with our coordinate system. I cannot emphasize this enough. So this is very important to move in the same direction, otherwise you may miss a minus. So from A to B, this would be then the integral from, let's say, 0 to 50 millimeters. Or let me just put it like this. It's from A to B, indeed, of Tx divided by Gj dx. Now, at A, x is 0. At B, x is 50 millimeters. Tx is exactly the equation we have up there. So it's minus, G and J are constant, so I will just write it like this. Minus 50 plus k over 3, x cubed dx. But also now we know this would be our k, so that would be 0.4 times 10 to power 6, or otherwise, you know, 4 times 10 to power 5. Okay, so that would be then integral of 1 over Gj, integral from 0 to 0.05 of, well, we can integrate it immediately. So minus 50 gives us minus 50x. This gives me x4 divided by 4, right? So I get minus 50x plus, you know, you get x4 divided by 4. But remember, this thing was 4 times 10 to power 5. So the 4s will cancel. So you get 10 to power 5 of x to the power 4. And then again, from 0 to 50 millimeters. And all you have to do is to insert this 50 millimeters here. If you insert 0, obviously you get 0, which is not a surprise. At 0, there is no angle of twist. It just starts. Or there is no relative angle of twist. It just starts, and then at 0.5, you get the angle of twist all the way to the end, which would be 1 over Gj times minus 1.875. Okay? And again, for this particular problem, we also know what is G and what is J. So G is 75 gigapascal. J is our usual pi over 2, c to the power 4, c being the radius, and that radius in this case is given as 4 millimeters. So if you insert these values, you end up with, let's say, a number for this, and that would be also a minus, a negative number, not very surprising, 6217 radian, or minus 3.56 degrees, okay? Does that make sense? So again, remember here what we do. If you think about this, you have a bunch of torques that are turning this thing in the clockwise direction in our coordinate system, right? So you expect that this point, with respect to this point, it turns clockwise, which is a minus number, okay? That's why at the end of the day, we expect that minus. I keep repeating this because, first of all, these are very important exercises, but also there is a little chance that you make a mistake somewhere, and you end up with a minus here and there. But I'm trying to say that there are various ways to check if this, if the procedure is right. Okay, so make sure to kind of run some sort of sanity checks on your results. Okay, if you look at the picture, you expect to see a minus value for your angle of twist. If you get a plus, it possibly means that somewhere in one of the steps before you have made a mistake. Okay, it helps a lot to pay attention to that. All right, do you have a question? Is that all? Okay, so I show you one more exercise. The next one is very, very simple. I think I said we will have two, but since we have a little time, let me just show you this. This is not a particularly complicated exercise. We just have a shaft, a circular shaft, as we usually do, and under some loading, we introduce a distributed shear stress within the shaft. Okay, so this is our very, very simple twist of circular shaft, and as you know, when you have one of these, you will get an angle of twist, and then you have a distribution of, let's say, shear stress, and it looks like this, and then you would have a distribution of shear strain, and on the outside you have your gamma max, and then on the inside you have your gamma that is related by R over C times gamma max. Okay, so this is your shear strain distribution, and we talked about this linear shear strain distribution. It always holds. Now, if it is elastic, then your tau is equal G gamma. So this immediately tells you that also your tau could be written as R over C tau max, which gives you a linear distribution of shear stress, okay? Now, pay attention. This one, linear shear strain, is geometrical. It always holds. It's always correct. But linear shear stress is only valid if it's elastic, okay? And this is all this problem is about. So we apply let's say, a torque to a shaft, let's say T, and then we want to know if that T is less than some maximum elastic torque, what is the relation between this torque and shear stress, okay? And then we exceed that in the second part, and we tell you, okay, in the second part, we have the angle of twist. We want to know also what is the, let's say, what we call the elastic core, what is the radius of the elastic core. So after you exceed your maximum T, so there is this thing T elastic, this is maximum torque such that the problem is still elastic. Okay? But if you apply a T that is larger than that, what happens is that if this is your circular cross-section, you will have an inner circle which is elastic. We call it elastic core. And then we would have the outer circle, which we call plastic ring. Does that make sense? Because we just exceeded we exceeded our maximum stress, right? So let's say if torque here could have been maximum, 500, sorry, if the shear stress could have been maximum 500, and then if you want to exceed that, well, obviously you cannot exceed that because that's your yield stress, but you lose that distribution or that linear distribution. What happens to your shear stress distribution is this. So inside your elastic core, you get the linear distribution, and then outside that, you get a constant shear stress that is equal to, yield stress, okay? So that means your tau max becomes your yield stress. And then this thing, it's called, let's say this is the radius of the elastic core. We call it Ry. Okay, so in the first part of the example, you are asked to derive an expression for maximum elastic torque that the shaft can carry. Okay, there are two ways of doing this. First of all, the relationship is given here. So if you say tau is equal TR over J, tau max would be T elastic, because we know that's the maximum T you can apply, and it's elastic, times C divided by J. And then this would be your yield stress. Okay? So that's it. So this becomes your relationship, basically. Tau max. Well, that's the relationship. That tau max is that. Or you can, okay, let's forget this. You can say T elastic is tau y times J divided by C, okay, which is basically the same relation. Okay? And if you use the relationship for J, you end up with something like T elastic equals pi over 2 tau y C cubed. So this is the answer to the first part, either this or this, it doesn't matter. Now, if you wanted this one, you could have also calculated it using our usual integral. So you can say T is integral of, let's say, distance times dF. And if you have a shear stress distribution, TF is tau dA, right? So you get integral of R tau dA. And remember we said tau is R over C, tau max. And we said tau max is tau y, so that's the yield stress. So you get basically integral of R squared divided by C tau y dA. And you can immediately recognize what's happening here, right? For 2a also you can basically, I mean, if you want, you can also write it as 2 pi r dr and do the integral, but also you don't have to do that. If you just look at this, you immediately you realize that that's Rj, okay, which gets us to the previous relation. Oh, okay. So the first part of the example is very, very simple. T elastic is simply pi over 2 tau y C cubed, or otherwise tau y J times C. And then you are given specific numbers and parameters for for the yield shear stress, tau y, and the yield shear stress, shear strain gamma y, which is corresponding to this curve. So you know what is this, you know what is this, and from their relation, you can also calculate the slope of the line, right? So G would be simply tau y divided by gamma y. So you would know what is also G. And then in the third part of the question, you are asked to calculate the angle of twist under that maximum elastic torque. Okay, so the angle of twist, you remember, it's simply TL over GJ. Now, T would be that T elastic that we just discussed. G is exactly this tau y divided by gamma y that we just discussed. And J, you know, it's pi over 2, c to the power 4, and length is given. So you can also calculate that maximum angle under elastic torsion, which would be 0.08 radian. All right? Okay, all these, let's say, first three parts, they are fairly straightforward, and it's kind of to warm you up for the last part. The last part is the only part that requires a little attention, and it's slightly different from what we have done before. And basically, the idea is to calculate the radius of elastic core if we have exceeded, you know, that angle of twist that we just discussed about. So we would, the question tells you this: we keep twisting this, and we reach 0.4 radian. Okay? So remember, the maximum angle that we could have had, and it would be still elastic, from part C, we calculate that, and that would be 0.08 radian. So that means if you twist it more than that, you enter into plastic zone. Some parts of your shaft becomes plastic. Okay? And then we do that here until phi is 0.4 radian. So if that happens, it's exactly this thing that I just drew before. Your shaft, it distributes into two parts. What we call, let's say, the elastic core in the center, and what we would call as plastic ring. But between the two, what we do know is that the shear strain distribution is linear. So this is gamma max. This is gamma y. So if this thing is your elastic core, right, it means out of this, you have constant stress, you have yield stress, right? So the maximum shear stress you can have here, it happens here, and that is tau y, which corresponds to gamma y, right? So this tells you immediately, or this gives you immediately the relation here that if you call this ry, that is the radius of elastic core, and then you know the radius of the whole thing is, let's say, c. This immediately tells you the relation that gamma y divided by ry is gamma max divided by c. All right? So in this relationship, you know what is gamma y. We don't know what is ry. We want that. The only thing that we need, well, we also know what is c. We yet don't know what is gamma max, but we know we are going to twist it with phi of 0.4 radian. Now, you should remember the relationship that we had before, that gamma max is c times phi divided by L. Okay, or if you remember, this was more like gamma equals r phi prime. We talked about this in the lecture, and then phi is constant, and because it's constant, you can actually write it as phi max, which is our angle of twist, times L, okay? Okay, so you have this relationship. Basically, it means that in this in this part, you have C phi over L. Does that make sense? Now, phi is given, that's 0.4. L is given. C is given also, but it also cancels out. And then if you just calculate that, your radius of elastic core would be 4 millimeters. Also, just for the fun of it, gamma max, if you wanted to calculate it, in this case, it would be 0.01. Okay? So shear strain here is 0.01. Here is obviously less. It's your yield strain, which is also given. So it's 0.002. It's 5 times smaller. All right. So this is, let's say, the third and the last exercise for today.